is a smooth bounded domain in Rn. Well, in fact, I'll mainly be talking about n equals 2 and n equals 3 for technical reasons. And I'm interested in problems minus epsilon squared, the Laplacian of u equals f of u in omega, u equals 0 on the boundary, and I'm mainly going to talk about positive solutions. And as you guess, I'm thinking of epsilon being small. And by omega bounded, I should say. Bounded and smooth boundary. So, now, the motivating thing is, we're not going to look at trying to understand all solutions, but we're interested in trying to understand solutions which are not too unstable. So what we're going to try and do is if you look at the linearized problem around the solution, you only look at solutions for which the Morse index is bounded. In other words, it's either stable or not too unstable in some sense. Now, it's known for many cases that in a lot of cases there's just far too many solutions otherwise. Also physically, the solutions you would hope to see physically are either most likely stable or certainly probably are not too unstable. So there's reasons for two reasons for it. Now, there's been an enormous amount of work on this. Now, technically, I'm going to assume FSC1. There's been a lot of work on these problems in recent years, and in many cases, we've got quite a good understanding. And in particular, the sort of assumption that's usually being done, I'm looking at positive solutions. I'll mainly look at the case f of 0 is greater than or equal to 0. And we assume that f has only nodal zeros. In other words, every time f becomes 0, that f crosses. It needn't be, it could be flat. But every time f crosses 0, it changes sign. And the main point of my talk is what happens if you drop that. Anyhow, that'll come back. Before I talk about the main thing, I want to talk about what's known in the case where f has only nodal zeros. And looking at positive solutions, we can understand things very well in many cases. If n equals 3, there's actually a technical condition which is probably removable, but no one's managed to do it yet. You want f to be not too flat at any 0. In other words, the technical condition that f doesn't tend to 0 is not of order, small order of y to the fifth at any 0. So it can't be very flat. That's a technical condition which should be removable, but no one can quite do it at the moment. So there's two results basically for firstly, and I won't state them too precisely. Firstly, what is stable positive? The first question you might ask is, what do stable positive solutions look like? This is for small epsilon. The answer is they're very simple. They look very simple. There's got to be a k, has to be a 0 of f. And what a stable solution must look like is it's approximately equal to k in all the interior, and it's got a rather sharp boundary layer near the boundary, near the boundary, the boundary layer is of order epsilon, and what the solution near the boundary, this solution looks like near the boundary, is you have a you've got to have a solution of minus v double prime equals f of v, v of 0 equals 0, v of infinity equals k. Using the first integral is at most one solution of that, and you can easily give a necessary and sufficient condition for that to come. And what the solution near the boundary looks like is, in fact, it's something like v of the distance of x from del omega over epsilon, and it's approximately equal to k inside. And what you're showing is saying any stable solution looks like this, and basically there's under very weak conditions there's a unique one. There is one proviso: you must be able to solve this. If this doesn't, you can easily write a necessary and sufficient condition down. A necessary condition is the boundary layer equation has a solution, but if you've got a node of 0 for which the boundary layer equation has a solution, there's a unique stable solution like this for small enough epsilon. So in a sense you get an almost complete understanding of the stable positive solutions under very weak assumptions. So the main work is in fact showing that any stable solution looks like that. Once you show that it looks like that, it's fairly classical techniques of sub and super solutions and things like that to show there's a unique one. And in fact, just a comment which will come back. What the main part of the proof is understanding you can give a definition of a stable solution on Rn, and the main part of the proof is understanding the stable solutions on Rn. That's the key point of that. So you get a good understanding. Notice what's interesting here. What this tells you, for a fixed f and omega, for small epsilon, the number of stable solutions actually doesn't depend on the shape of omega. So you get so the number of stable solutions is independent of the shape of omega. As distinct, if epsilon's not so if epsilon's small, the shape doesn't matter. Notice if you go the other way, if you fix epsilon and vary the shape of omega, the number of stable solutions then may well depend on the shape of omega. Now, the typical examples, which I'm not going to explain in detail, is you look at things like dumbbells, something that approximates to a domain that approximates 2 balls, or approximates 2 pieces. So we understand the stable solutions in this case rather well, and we also can understand if you bound the Morse index of solutions, we can understand those fairly well under a technical condition which won't run out. The only thing that can happen is you can put a finite number of, if you bound the Morse index, the only difference from a stable solution is there's a finite number of sharp peaks on top of the stable solution. And one of these peaks are given by, the extra peaks are given something like phi of x minus k over epsilon. This is the peak, the extra peaks. And the number of peaks is at most the Morse index. So if you bound the Morse index, you bound the number of peaks. Where in fact a peak looks like this, where minus Laplacian of phi equals f of phi. Phi is positive, phi is greater than b, and phi tends to b as norm x tends to b. So it's, the peaks are determined by an equation like this, and in fact they're determined by radial solutions of that equation. Under very weak assumptions you can show that the peaks are determined by radial solutions of this equation. So even the finite Morse index solutions, you can understand them very well. There's one technical condition I won't write up to prove this second one. But there's still in the case of multi-peaks, the location of the peaks is not completely understood. In the case of one peak, the location is more or less completely understood. But in the case of multi-peaks, there is still some questions there which are not understood. So we have a fairly good understanding of the solutions, what these solutions look like in the case of there's no nodal zeros. So the question I'm mainly talking about today, let's say we have a nonlinearity which does something like this. Let's draw one. So it might start off positive. Then it might go something like this, where it has a non-nodal zero. You might ask why I choose that side. If it has a non-nodal zero coming from below, that tends to have no effect on the equation. So the interesting case is got a non-nodal zero where it's positive on both sides. Because the other one, it turns out, doesn't produce solutions. And the question we're going to try and understand is how the stable solutions behave, and more importantly, how the finite Morse index solutions behave. And as in the title of my talk, it turns out they're affected by a slightly unusual limit problem, which surprised me, and I really realised it came up. So in fact, in some sense, most of the differences occur for the finite Morse index solutions. It turns out that this picture of the stable solution, the picture for the stable solutions, is still largely true. It's basically true. Well, except there is one difference that does occur, which also occurs for, in fact, if there's even if there's only nodal zeros. Now, if you've got a stable solution, it looks like this, with a sharp boundary layer, and then it's very flat up top. The natural question is, where does that stable solution have its maximum? And in the case of K is a simple zero of F, the answer is well known. Of F, it occurs maximum of the stable solution occurs at a point of omega of maximal distance from the boundary. Distance from the boundary. So it's a nice geometric condition. From the boundary. So it's determined purely by geometry. Of course, if you are lucky in your domain, there could be several points of maximal distance from the boundary. Then you have trouble. So that I'm not going to go. I think this is first proved by myself and Jinshin Wei a long time ago. But and there's one thing that is, I want to, for reasons of comparison, I should mention in this case, it turns out the slope of the stable solution, which I call U epsilon minus K, is exponentially small. So notice in this case, where the maximum occurs is almost completely determined by the geometry. Exponentially small in epsilon. The last point will make more sense. So what happens if we've got one of these flat zeros? And it turns out, now let's assume we've got let's call this zero, say S. So as we've got f of s equals 0, and let's assume that f prime of s is asymptotically like sine s, f prime of x, sorry, sine x minus s times mod x minus s to the p minus 1 as x tends to s. And for the stable solution, you only actually need it from below. Now, if that's a natural assumption. There could be a positive. Let's put a C in here, where C is positive. That's a natural assumption to have if you've got a non-nodal zero. And as I said, the theory modifies very easily to show there's still a unique stable solution near this point. But what happens to the location? And it turns out the location now is, by the way, I should say here, P is bigger than 1 if it's if it's C1. P has to be bigger than 1. To get the location, we get the asymptotics of u epsilon. What u epsilon looks like is, let's call this, it's s minus epsilon to the alpha v of x, where, what is v? Where v is a solution of, and this is where of the problem, of Laplacian of v equals v to the s, v to the, sorry, my mistake here. It's cv to the p in omega. V tends to infinity as x tends to go up. So the asymptotics are v, sorry, one more condition, v is positive. Now, a couple of comments. Firstly, this problem has a unique solution. There's been a lot of work on these problems by a lot of people over a long period. Now, plus, I should say, plus small order of epsilon. Now, near the boundary, I'll just make a comment. Now, that's not probably not. Now, near the boundary, I have to modify these asymptotics because, in fact, near the boundary, it still looks like this. But near the boundary, it looks like this still. But it turns out, if you check the calculations carefully, near the boundary, this matches up nicely with this. So what as you can guess then, that the maximum of u epsilon is close to a minimum point of v. And that's by the way, the title of the talk was the connection with this equation, which was the unexpected one, I think. So in fact, you could. It's not as nice as the previous case because you can where the minimum occurs isn't affected by c. You can just scale it out, but the location now is where the minimum occurs is determined by a partial differential equation. And it's not so easy to understand this, where this minimum occurs. You can say a few things. There's still there's some cases you can say, if you've got something, there's still a Giudice-Nieremberg type theorem for this problem. For example, if you've got something like, I'll just draw like an ellipse, which has got lots of symmetries, I'll draw this one, then you can show that the minimum occurs at a point like that, the actual point, because the solution of this problem has to have the two is actually it has the two symmetries, and it's decreasing along here and decreasing along here. And so it's known that there is a nice moving plane. You can make moving plane arguments work quite a lot of the time for this equation. So in a lot of nice domains, in fact, the answer is still the same, but it's not always the same. If you take some form of ellipse where this is shorter than this one, and round this corner up just a little bit, should just shorten that side. Now, this is still going to be the point of maximal distance from the boundary. So for the simple zero case, you can show that the maximum, at least the first order, doesn't move. But on the other hand, the solution of this, the minimum moves slightly to the right. You've got to use moving plane arguments. So the location. So this, you can use this to give an example where the location of the minimum of this, and so the minimum, the maximum of u epsilon is different from the case here. So it really is a different point. But we don't really understand so well where this occurs. It's not even clear how this depends on p, how the minimum depends on p. Once there's conjectures, but it doesn't seem quite so easy to prove, that as p goes to 1, the minimum of s goes to the point of maximal distance from the boundary. But that doesn't seem to be so easy to prove. The basic problem is, for p equals 1, this equation has no solution. Because for p equals 1, you've got limits on the graph. So taking the limit as p tends to 1, there's a change in the nature of the problem. So it doesn't seem quite so easy to do. So anyhow, what is interesting here, I think, is that this occurs naturally as a limit problem, and it's not going to be for the last time. And notice, by the way, there's another difference. U epsilon is only algebraically close to S. And sorry, I should have said alpha is 2 over p minus 1. So in this case, U is only, the solution is only algebraically close to S. In the simple zero case, it's exponentially close. Sorry, I've changed my note. Sorry, it should be, I've got a K here. I changed my notation. Sorry, that's a K. So the differences in the stable solutions is not so different, is not so much. But what we're going to see more differences if we look at solutions whose bounded Morse index. Let's make that K. I'll vary my notation. There's going to be a stable solution, U epsilon near this point, and a second stable solution, U epsilon tilde, near this point. So we've got two stable solutions which are in fact ordered. So, now the first comment is there's got to be a solution of Morse index 1 between these two, but you can just do a mountain pass between these two. So there must certainly be one solution of Morse index 1 between those two. So there's a non-empty class of finite Morse index solutions in between these two. And what I want to understand is the solutions that lie between those two of bounded Morse index. So what I'm interested in is solutions U so that U epsilon is less than or equal to U is less than or equal to U tilde epsilon. And of bounded Morse index. and it turns out there's basically only, under reasonable conditions, there's only 3 possibilities. Remember, I stress I'm assuming n is less than or equal to 3, although sometimes I can do n equals 4. What can bound solutions of bounded Morse index look like? And notice it's not the empty class. As I've just said, there's always one in Morse index 1. The first possibility is basically they look like U epsilon, same sort of asymptotics as this, except let's give this a name. And sorry, let's change this. Didn't affect what I said there. I should put an absolute value in there. It doesn't affect what I said there, because it was a positive solution. I want to look at changing sign solutions. Looks like you accept V, let's call this a name now, is a changing sign solution of stuff. Sign solution of stuff. That's the first possibility.
So you mean the maximum U is between the U epsilon and the U epsilon 2?
Yeah, that's right. This is a changing sign solution. This one will get above.
You started with the issue boundary position.
Yeah, but remember, it's got the boundary layer still.
Okay.
Yeah.
In the first line, you wrote that U is between epsilon.
Yeah, these two are. It's between these, so that forces it to have 0 boundary condition. So the first possibility of solutions, which this case will lie above U epsilon, because, no, I should point out here, the positive solution of this is the maximal solution. Every other solution of this, rather than the positive solution, is less than or equal to the positive solution, which means that these other solutions will produce something above that. That's the first possibility. The second possibility, and notice in this case, these solutions have norm. In fact, in this case, the norm of the solution minus k is of order epsilon to the alpha. The second possibility is that the norm of U epsilon minus k has a positive lower bound. And in this case, U epsilon, U minus U epsilon looks like a rescaling of a solution on Rn, of a solution of finite Morse index, which I'm not going to define precisely, of minus Laplacian of V equals f of V on Rn. V is greater than k. V tends to k as norm x tends to infinity. And in fact, and V is radial. It turns out finite Morse index solution to this have to be radial. So in fact, what this, and it's a scaling, is it looks, you take the solution of this and rescale it. It looks like V of x over epsilon. A rescaling. It has a sharp peak. Picture is, it looks like the picture in the first case. These solutions have a sharp peak. So they're close to, and there could be several sharp peaks again. There could be several, you could have several peaks like this. So in many ways, it looks like the solution of finite Morse index the first time. It's this plus sharp peaks on top. So that's like the first case. There is one, and these are the main two cases. The third case can only occur if P equals P star equals n plus 2 on n minus 2. And here, it's in between these cases. We have that u epsilon minus k tends to 0 as epsilon tends to 0. All my norms are infinity norms. And it's in between norm u epsilon minus k over epsilon to the alpha tends to infinity as epsilon tends to 0. So it's size in between, intermediate between the other two. And rescaled, it looks like, and shifted by k, it looks like a solution, the critical exponent equation. Minus the plus even v equals v to the p. V is greater than 0. V tends to 0 as norm x tends to 0. After rescaling, you've got to add a k. Take a solution of this and add on k. So it looks like that's the p star. Critical exponent. Remember, the p star is n plus 2. P star is n plus 2 on n minus 2. So these are the only possibilities. Now the interesting thing here is which possibility occurs depends very strongly on the p. Remember, the p was the how fast the function decayed at the point k. For example, and firstly, if p is less than or equal to n over n minus 2, which means always if n equals 2, only case 1 occurs. 1 occurs. Now notice the solutions in case 1 don't look very asymptotically. At the first order, don't look very different to the stable solutions. So in this case, and in fact, you can go a little further. Basically, you can prove case 1 occurs, because you show this case can't occur. There's no such solution to this one. And in fact, and also for similar reasons, if n over n minus 2 is less than p is less than n plus 2 on n minus 2, and the function f of x minus k over x minus k to the p decreases for x greater than k, the same thing is true. If you look at the picture, that's not an unreasonable assumption. Remember, our function from k starts off flat, goes up, and goes down like this. So it's not a completely unreasonable assumption. So, and basically you can prove, these results. It's basically, you can show case 3 can't occur. There's p is not the critical exponent, and case 2 can't occur because there's no such solution of this equation. So p is relatively small. It's always case case 1. On the other hand, if p is bigger than the critical exponent, and only there is a nice symmetric domain, well, sometimes called a Giddens-Nieremberg domain, case 2 occurs, case 1 occurs. Sorry, but case 2 occurs, sorry, wrong way around. Because you can show that there's no such changing sign solution of this equation. In fact, p greater than or equal to. Now, why is that? If you've got a nice symmetric domain, I'll just draw the picture, but I'll draw the picture as a 2-dimensional ellipse, although it has to be in 3 or more dimensions. if you've got something like an ellipse, if you have our solution of our equation preserves the symmetries. Its changing sign, solution of this equation actually preserves the symmetries. If it's changing sign, and it also has nice increasing properties. So, in fact, the set of points where V is less than 0, you can show is star-shaped. Because of the, and then the point is, then for V less than 0, you're just getting, and you take minus V, you're getting a solution of this equation on a star-shaped domain in the inner piece. And that, of course, is well known to have no solution of P is bigger than P star on a nice star-shaped domain. So if only has got enough symmetries, this piece has a star shape. This is the part where V is less than 0. And so we can just, if you put W equals minus V, we've got a very familiar equation, which has no solution. So, well, basically, we can, the way we can understand which cases occurs is eliminating the others. So all cases can occur. And notice that the P affects a great deal which case occurs. The only way you prove case 3 occurs is, in fact, showing there's examples where neither of the other two can occur. So, so you can, if you choose, you can choose examples with the sort of arguments I gave, show that neither of these can occur, so case 3 must occur. Now, just some comments on the proof. As you might guess, it's a lot of, you look at scaling arguments and limit problems and things like this all the way through. And also you use lots of sub and super solutions, which you use very much in the proof of these theorems anyhow. And also, for technical reasons, we know we have to prove a new moving plane argument, where if we have solutions of equations on a half space, we've got, say, minus the plus in V equals G of V on a half space, and I'll draw the two-dimensional one. When, rather than putting a Dirichlet boundary condition on here, we assume that V tends to infinity as x1 tends to 0. And in fact, fairly uniformly. And what we can prove a moving plane result is says if you have a solution like that, it's got to be strictly decreasing in x1 for x1 positive. In particular, it can't have a minimum. So we need a moving, that's needed in the technical part of the proof. Now, this is needed in analysing solutions of this close to the boundary. You can see infinite boundary values might occur because of this thing. So it's a new moving plane that is needed for technical reasons. So it's a mixture of scaling and limit arguments and very careful choice of sub and super solutions. Because it turns out we need very good estimates of how these solutions behave relatively close to the boundary. So now, so you can, a couple of comments on this. It tells you that maybe you need to start thinking about the multiplicity of changing sign solutions of that problem. Because in fact, under reasonable conditions, you can prove that any changing sign solution of this tends to yield a solution of the first type. So, and in fact, under technical conditions, you can show that each one of these yields a unique one. So, so the multiplicity of that changing sign solutions doesn't seem to have been studied before, but it seems to be a problem that's now worth looking at. Now, this is problems and nuisance. There's a useful remark here. Remember, this problem has always got the positive solution that's U. Infinite boundary values are a nuisance, even though you can get good asymptotics of these solutions close to the boundary, which is well known. and is part of the proofs there. In fact, it's hidden in the proofs. But if you want to look at changing sign solutions of this, it turns out if you the boundary values simplify somewhat. If you have two, if you look at two, you've got the, say U is the positive solution, and you've got another one. It turns out that U minus V, if V is another solution, U minus V tends to 0 as X tends to the boundary. So if you want to study this equation, it's much easier looking at the multiplicity of solutions of this equation to look at the difference with U, because then you get a much simpler boundary condition. So instead of having an infinite boundary condition, if you look at a difference, then you get a Dirichlet boundary condition, and that is rather easy. You do pay for it because then some of the coefficients in the equation become singular. Now, because if you look at the differences, you're getting equations with singular coefficients, but that actually seems technically easier to do. And the other thing I should say, and the proofs, I forgot one thing. If the proofs of this depend also on in very careful techniques if you have rough approximation solution, if you have very rough approximations to the domain, how the solutions change. You have domain variation things where you vary omega in a rather rough way, even for linear equations. It depends on the theory of that. And you might ask, and related to that, if you're looking at changing sign solutions to this, you might ask, is the answer very simple? The answer is it's not very simple, unfortunately. And as you might guess, the standard example where it's not simple is if you look at domains, not surprisingly, I've heard it talk before, looking like this. It's rather more technical than usual, but let's look at a domain like this. It's like something, it's like sort of like two ball-like objects with a very narrow net. You can show that that you can have solutions of an equation like that which are not symmetric about here. It's rather more technical than the classical case. So there's in fact going to be at least 4 solutions. There's the positive solution. There's another solution that's symmetric across this axis. But you get at least two more solutions which are different, which are not symmetric about this axis. If you have one, you'll get the other one, just by reflection. So in science, not quite the way you do it. In a sense, what you're doing, at least intuitively, but in practice, if you've got, think of these, on this one domain, one of these two domains, there's 2 choices of solution, the positive and the changing sign. I better draw this to look a bit more light. And there's the positive and the change. On the other one, there's a positive and a changing sign. And there's at least 2 choices here, exactly 2 choices on a ball and 2 choices here. And you might guess, well, it's rather technical to prove, if you open it up, there's 4 choices. So you're going to get 4 solutions. So unfortunately, the number of changing sign solutions of this is not so simple. And which means the multiplicity theory is not going to be quite so good. I might point out whenever you have a solution of this, the solution you generate this way is finite Morse index. So there is a theory. I should point out this one is much harder than the classical one with 0 boundary condition. It gets much more technical. So but there's lots of things we don't know. But certainly we got no understanding at all of the multiplicity of this, and what I don't know, which I suspect is true, there should be examples where these 2 occur simultaneously. It seems unlikely it switches one from one to the other. So it looks all likely that that there should be examples where both types of finite Morse index solutions occur simultaneously. But I don't know examples of that. And I think the most intriguing thing about this all is that this appears as a limit problem. And that's a good place to stop.